Cool. So good afternoon, everyone. First of all, thank you very much for turning out here at the end of the Thursday of ODSC, and thank you very much to ODSC for giving us a chance to present some of our work today, and also talk about what we at Prowler.io and what I believe is a really important topic as a data scientist, but also working within AI generally. So that topic is about making robust decisions, so making a strong, safe decision in an uncertain world, especially an uncertain world where you don't see that much about what's going on. So as was mentioned, I'm head of data science at a company called Prowler.io. You may not have heard of us because we're relatively young. We're a startup in Cambridge, and our kind of remit, our purpose is about building a platform for decision-making technologies working across different sectors. So today I'm going to be talking about one of the applications that we've been doing within supply chain management, but really it's about, you know, our kind of philosophy is that actually decisions at the end of it, there's only so many different types of decisions that you need to make in the world. And actually the underlying problems, whether you're working in supply chain or whether you're working in energy grid distribution problems, are actually kind of similar, and how that maps out against other sectors as well. So there's going to be 4 things that I'm going to talk about today. The first is what happens if you go to your data store and there's not as much data there as you were hoping. The second is about probabilistic models, why we might need them and how they work if you're not familiar with them. The third is about a robust decision. How do you make a decision that is perhaps not the best for it a posteriori, but given the a priori knowledge that you have, certainly would kind of put you in the best position. And in order to kind of bring all those points together and actually give a real-world example, I'm going to be talking, as I mentioned, about an application that we did within supply chain management. So, the first statement that I'll say is that not all big problems are solved by big data. And in some sense, that's, I think, a little bit contentious as a data scientist, because I think there's a kind of a feeling out there that, oh, you know, data scientists, we're there because there's so much big data and we don't know what to do with it. Actually, I'm going to be talking about some situations that that's not the case. So why I think this is even a problem in the first place is that traditionally, historically, we've always been, you know, for the majority of humanity's experience, we've always been in a data deficit. And then suddenly we're working in this time of data deluge. What do I mean by that? Well, if you think of cuneiform tablets back in prehistory, you know, okay, very difficult to maintain, very, you know, not very cheap, but not also didn't sustain, didn't persist. Then all of a sudden we, you know, have printing, we can write on paper, we can store the paper. Okay, it's there, but again, it's not the best case that we have. And then what I think is really interesting in kind of the late 1990s, early 2000s, this is the time, yeah, okay, we had computers before then, but in the early 2000s, this is when it became really cheap to store data, it became really cheap to record data, and also became possible to transmit large volumes of data. So this is when this age of big data started, and it's quite interesting to see when, you know, this term of big data and also, you know, the cost of a hard disk space against time. However, I don't think just by throwing, you know, having data everywhere is going to solve all of our problems. And I'm sure as data scientists sitting out there, you've probably experienced that yourself. And I think there's kind of 2 main cases where it really trips us up using a lot of the kind of toolkit that's traditionally out there. The first challenge, as I see it, is that actually quite often we're given many, many data points, but there's also many, many combinations. So here's the example that I'm going to give you. So let's think about the traffic among shipping routes around, among the world. So millions of shipping journeys are made each year. Great, fine. And consequently, we can expect to have a lot of data for that. Fine. However, there are thousands of shipping route combinations because there's many thousands of shipping route combinations because there are many thousands of origin ports and many thousands of destination ports. So actually, when you receive all these millions of rows describing all the years worth of data of shipping routes, actually, if you're then asked, okay, well, how much was shipped, or how much do you think will be shipped between Shenzhen and Felixstowe? Well, if you go back to your millions of rows of data, you might find that there's only a very small proportion that fit that route. And even worse, if you go like both Shenzhen and Felixstowe big ports, actually if you go for smaller ports, you find that there's even less. You can go, well, okay, well, I'll just infer it. I'll apply these methods that will, work out globally what's happening. But actually, that might not be sufficient. And in a lot of cases, what's happening in one case in your data is not going to explain what's happening elsewhere in the cases that you're really interested in. So the lesson there, as I see it, is that the data set as a whole is big, capital B big. However, the number of combinations is also capital B big. And when you divide a big number by another big number, you're not always guaranteed to get another big number back. So in reality, it often is going to be the case that there's only going to be a small set there that's going to be of interest to you as a data scientist. So that's challenge number one. The challenge number two is that not all data is directly observable. So what do I mean by that? Well, if you're trying to infer what's happening in a city, you have thousands of different types of measurements, but actually you might not have the type of measurement for the thing that you're most interested in. So I've used this example from smart cities. You can also use it for very large, complex pieces of machinery where it's not practical, it's not feasible to plug a little sensor on every single piece, but maybe it's the piece that you can't see that it is most important. Another example is, in my prior life, I was a computational neuroscientist. As somebody who worked in the physical sciences, for me, it's actually quite normal to think about things, to look at phenomena that you can't directly observe. You have to infer it somehow. And last of all, the example that I'm going to be diving into a little bit later today is exactly about this too. So this is going to be talking about pallets. And they're just like 4 examples, but there's many, many, many more. So what I'll say is that real-world challenges are often complex and suffer from poor visibility and available data either being sparse and sporadic, missing, partially observable, not directly observable, or a combination thereof. And that this isn't limited to just one type of sector. So what I think is interesting, though, is that the business solution is, we're just going to do big data. We're going to do big data analytics. We're going to do IoT. We're going to do Internet of Things, and that will solve all the problems. I don't think it will, because fundamentally these sorts of paradigms are really, not suited for sparse data approaches, and they're not going to be efficient as well. I think this is the other thing that's really important. We talk about big data, but actually doing the sorts of computations and the sorts of algorithms that are typically used, especially for deep learning approaches, really aren't efficient, both in terms of time and both in terms of energy. So the challenge is then, how do you get around sparse data? So if we were to zoom out and go, well, if we've got a sparse data system, what would our model wish list be? Well, our model wish list probably would be, models should, note the word should, be able to robustly capture dynamics across a range of situations. They should be able to scale well, efficiently by using data, and data that can be sparse as well as dense. They should be able to adapt correctly to updated information. And I think if I said those three things, I think broadly everybody in this room would agree. I don't think there's anything there that's really that contentious. The thing that I think that I'm going to throw in there that I don't think is usually on most kids' Christmas lists for models is that I think it's actually really important to represent uncertainty in our model and our environmental noise too. So there was a talk yesterday afternoon exactly about Gaussian processes by a researcher at Bosch, and she gave a really nice introduction, a very thorough and deep introduction. I don't have time to go into all of that, but what I will say is that these sorts of problems are exactly where we want to be. These sorts of approaches is exactly where we want to be placed. So the solution is, one of the solutions out there, the one that we use at Prowler, is this idea of, if you want to have to capture certainly those first 3 points, is that you should be first 2 points. Is that you can use Gaussian processes. So this is a type, a fundamental type of process that is non-parametric, so it can represent functions, which means it can represent, deep complexity of the world and really capture some of those real-world dynamics that we see. They are very data efficient, and what's more, they are explainable. There's no hidden weights in there. The weights in there represent phenomena that you might see in the real world, and I'll talk about some of the challenges that brings to. Gaussian processes by themselves are not enough, so we combine them with Bayesian inference. Bayesian inference really captures that points 3 and 4 there, so they allow us to adapt, and they allow us to represent uncertainty about the world too, or about the model. So, yeah, they update as new data becomes available. So just kind of a really brief introduction if you're not familiar with Gaussian processes. So as I mentioned, this is a type of probabilistic model. So let's say that we had this, this is the true function of some sort of relationship between, let's say, a function, a position in space and time. So this is the real function, but we don't see that. We only see something that's been sampled from that. And it's sampled, it's because it's a noisy world, the sample's a little bit noisy too. Okay, so what I'm going to do then is, using just those data points, I'm going to come to it and say, well, okay, I've got all these families of kernels there. So kernels themselves are really just covariate functions, and they describe, somehow, in one sense, they capture the dynamics, and in another sense, they're going to provide a kind of a thumbprint for us to use. So what's great about them is that if you use different kernels, so different combinations of covariate functions, you get different fits. So if I was to pass these different sorts of, if I was to use Gaussian processes that were fit with these different kernels, I would perhaps get fits that look quite different from each other. And I think you can say, well, okay, automatically as a human, I can look at this and go, okay, well, some of these fits clearly capture the dynamics better than others. And that's certainly true. And in the next slide, when we talk about Bayesian inference, we'll come to how and why you decide which kernels are the best. But the point here, I think that's really important, is that there's 4 reasons why Gaussian processes have advantages here. The first is that they are extremely versatile. That you can use there's a couple of mathematical constraints, but really you can use any kernel. You could use, as long as it's positive semi-definite, you can use any function to describe your kernel function. You can also use combinations of kernel functions. So here I've chosen some kind of, very slow sinusoidal, a combination, and something with a slightly higher frequency. They don't have to be periodic. They don't have to be, you can have noisy, you can have Matern 5-2s, you can have all sorts of functions, and you can combine them as well. So that's one of the things that makes them extremely versatile. The second is that they're extremely data efficient. And the reason for that is because a lot of the dynamics are captured in the kernels, so when it comes to fitting them, they're already there. You don't have to spend the time training the algorithm to fit these dynamics because the kernels already capture that information for you. The third reason is that they are both transparent and explainable. The kernels themselves already then contain some sort of representation about the dynamics in the system. So, for example, if you have a kernel in there that has a periodic function, well, that's going to and that's the one that fits the best. That's going to tell you that there's some sort of periodic noise in your signal. And of course, if you want to, be clever in the way that you choose your kernels, and you know already ahead of time that there's a periodic signal in your periodic signal in your data, you can already incorporate that in. The last reason that I think is really important is that they can quantify uncertainty. So what we can see here is that in each of these cases here, the dark blue is the median, and this lighter blue region is the 90% confidence interval. So what I can see in looking at all of these fits from left to right is that in this case here, I would say no, okay, as a human, I would say it's not a good fit because I've got these large regions of uncertainty that actually correspond to where it didn't have any data, but the uncertainty around that just blows up. And you can see, for different sorts of kernels, I get different sorts of fits, and automatically I get information about the amount of uncertainty that the model has about that fit. So, as I mentioned, Gaussian processes are only half of the story here. We really need this other half, which is Bayesian inference, which allows us to certify that uncertainty. So, just to run through quickly how that works, so when we first come to the data, we will be completely uncertain about the mapping. We can go through and say, okay, well, we'll represent our belief about what the underlying function is, could be using probabilities. So here in that example before, I had 3 different sorts of kernels. I'm going to just assign a starting probability to each of those. I'm then going to update my beliefs, these probabilities, after seeing that data. And I'm going to downweight our belief in functions that are inconsistent with the data. So I'm going to throw them away. However, I'm going to upweight any of the functions that do fit with the data and that are consistent with that. And then I'm going to keep on repeating as I get more and more information. So by the end of it, you should have a really, your Bayesian inference will allow you to have the best fit that is possible for that data, because really what it's telling you is, given the data that you have here, this is the best that the model could do. Or conversely, it's going to tell you that, it's going to answer, is the model consistent with what the data suggests, and vice versa. So I've tried to be as high level as possible during this talk. There are 2.5 formulae in here. This is the first one, but really, so this is where the Bayesian part of it comes in. So what this is saying is that, okay, this posterior, this fit that we see, is the probability that the parameters are described by the data, and this is a function of the probability that the data is described by the parameters, given the probability of the parameters and given the probability of the data. Very, very simple, but very, very powerful. And if you speak to the mathematicians in our company, they are very excited about Gaussian processes and Bayesian inference for the reason, many reasons, but one of them is that Bayesian inference is a very powerful and very elegant approach for the reason that if the prior is a Gaussian, the Bayesian inference preserves that, so then your posterior is also a Gaussian too. So this allows you to do some very nice work when it comes to making modifications after you fit your data. So the two things that I'll also say is that I think there's also a bit of a pushback that we experience when we talk out to companies, or that when we talk out to businesses. There's always this kind of feeling that, well, uncertainty, that just means that you don't understand the problem very well. You're not predicting very well. You're not understanding what's really happening. Your models are broken. And I would say, okay, no, uncertainty is a feature. It's definitely not a bug. And there's two reasons that I would say that. So the first is that if you have a space, and whether that's a state space or a time series that you want to investigate a little bit further, uncertainty will allow you to go through and say, okay, where should we focus? Where should we get more data within this space? And what you can do is, if it's very expensive to have a recording at each point in time, using uncertainty will allow you to go through and say, okay, where is my uncertainty highest? Okay, well, if it's where it's highest is where I should go through and have a recording. So to kind of motivate that, this is an example of just a really simple Gaussian process being fit by Bayesian inference. And what you can see here is when it starts is that, okay, we start off with a large array of kind of prior samples. And what it's going through and doing is it's going, okay, I'm going to choose a data point at the point where my uncertainty is the highest. So you can see, okay, it's going through and it's measuring first here. Sorry, if you kind of watch it, you'll see it. Each orange point is an additional recording that sample that it takes. So here the uncertainty is high, so it's going to compensate for that by putting, making a recording at the point where the uncertainty is the highest, and keep on going through and repeating that until we're fairly certain about what the underlying function there is. So that's one example where it can be useful. The second, I think, is perhaps more relevant to many of the challenges and problems that we probably work on in this room. So the second is, how confident are we about a future prediction? So the way that when I showed those three examples of three different kernels giving you three different fits, what we saw is that there was kind of different amounts of uncertainty for each. The way that you can quantify that uncertainty is using marginal likelihoods. So I'm going to motivate again by another three examples. So this is data from the Mauna Loa Observatory. This is CO2 atmospheric recordings. And you can see that it's rising over time, but there's also this periodic function that is to do with, it's higher in summer than it is in winter. So if we were to go through and fit a model to this, if we have a very simple kernel that is just using the standard error, it's going to come back and it's going to give us a terrible fit. And what you can see is that the uncertainty there is very high. So the marginal likelihood correspondingly is very, very high, because it's the prediction is not being well fit by the data. If we use different combinations of kernel, what we see is that, okay, the fit is better, that uncertainty bound is a lot lower. It's still, quite high, but it's definitely lower than it was. correspondingly, the marginal likelihood also comes down too. Finally, if we actually choose a kernel combination that makes the most sense, what we see is that we get a really nice fit. There are uncertainty bounds in there, but they're so small that you can't really see them. And if we were to plot that against the original data, you'll see that it fits really, really nicely. And of course, we do this during a backtest step, and then we kind of go through and continue on and see what happens. So I've talked now about probabilistic models, Gaussian processes, and uncertainty. And try to make a case, I hope, for why it's important, or why uncertainty can certainly be a feature and not a bug. And I've talked a lot about forecasts, but one of the things that I wanted to talk more about was actually about decisions and making robust decisions. So how do those two things work together? Because a forecast is not a decision, is it? And I would say no, directly it's not, but they're really important for making a decision. And uncertainty is a major factor in that too. So why is that the case? Well, again, let's zoom out a little bit and look at the big picture of what we're trying to do. So if we were to look at 4 levels of AI, and I'll explain where they came from. So these actually were put together by the head of UX at Prowler, so Mika Meskinen, who gives a really nice framework, I think, that kind of puts into place how predictions and forecasts fit in with decisions. So in terms of stage 1 of AI, we can think about a model as being, or a system as being a predictive system. It just tells you what's going to happen next. It doesn't make any recommendation, or it doesn't give you any decision along there. So this can be something like a weather forecast, right? Tomorrow it's going to be 21. It's up for you as the human user to decide what you want to do with that information. So that's predictive AI. The second level is instructive AI. So it tells you it's going to be 21 tomorrow, but it also tells you there's going to be a 50% chance of rain, and you probably might want to use an umbrella. The third level is integrated AI. So it already has the umbrella by the door for you. And the last is autonomous AI, where the human user in that loop is very, very small. It's negligible. It's really just to kind of overwrite and check for major errors. Really, at this, so what you can see here is that as we go, further to the left, further to the right, we become more and more autonomous, and we move from a prediction through decisions where the humans are in the loop, or the human user is in the loop, to an autonomous system that requires marginal interference from a human user at all. So, in terms of where, as a company and as a data scientist, I believe that the biggest impact is going to be, I believe it's going to be, decision making is going to be the part of AI that has the biggest impact, and that's going to be stages 2 to 4. And the question about whereabouts on that spectrum you want to lie really depends on, I think, a lot of things. Confidence in the system, ethics in the system. You can think of autonomous cars as being an example for that debate space, but also very much the user case too. So if we're talking about decision-making being an important part, well, okay, the caveat then is that if you're going to make a decision, then the decision-making aspect of it has to be built on an informative prediction. Note here that I say informative and not the best, not the most correct. So the reason I say that is because the systems, that have 99% prediction accuracy, fantastic. There are no systems out there that have 100% prediction accuracy. Because if they do them, they become actually a very trivial thing to forecast or to predict, right? So there's always going to be some margin of error. So I'd rather know what that margin of error is, or that margin of uncertainty is, and then use that in order to inform actually, given that, what's not the best decision I could make, but what's the most robust decision that I could make. So what is a robust decision then from a, I think as in a layman's term, we all understand what that, we have an intuition about what that means. What is it from a mathematical viewpoint? So it's one that maximizes gain or minimizes risk. You can use this interchangeably. You can just reverse the sign, whether it's gain or risk, over a course of all potential outcomes. So in the case here, again, another example, what we have is that if we have a system of data points and we go through and we fit a function to it, but we say, okay, well, actually, I want to know what the next data point is going to be at some future time. Okay, well, then I can say, well, okay, I'll go through and fit some sort of function, and maybe that's just using some sort of simple regression. It doesn't have to be anything fancy. And I'll say, okay, well, at this point here, I think it's going to be this point. But the question is, okay, well, what is the value that we predict at time t? Well, it's going to be that, I think. But if there's a cost or a reward associated with that time point, well, actually, how does that also vary within this space too? What that really means is, okay, well, what's the reward if I get it right? Or conversely, what's the cost if I get it wrong, right? So an example of that can be, one of the things I talk about is it's symmetrical. What I mean by that is, if I overestimate, is that worse than if I underestimate? If I say it's, 1.5 and it's actually 1, is that worse than if I'd said it was 0.5? How does that relationship work? Secondly, is the cost function dependent on other spaces? Is there some sort of global cost function in there too? That's actually not dependent on whether I get it, over or underestimated. So what I can do instead of just having like a simple regression, I can go through and say, well, okay, actually I'm going to apply and look at the uncertainty around my prediction here and say, well, okay, well, at this point here, I think, it could be, I think it's going to be here, but it could be actually, I'm pretty certain it's, with 90% confidence, I think it's anywhere within here, within this range. Okay, so, and that's important because if we know the likelihood of the outcomes, we can then choose the outcome that will maximize our potential, maximize our potential gain. To kind of give, delve into what that means, we want to find the decision that maximizes the expected reward. And formally, second formula of the afternoon. So this is what we're saying. So we're saying, okay, well, actually, I want to maximize, the reward of all actions given all the rewards that's available. And I want to make sure that that's maximal over the entire space as much as possible. Okay, so if I go through and say, well, okay, well, if this is my median and this is my 90%. Upper and lower 90% confidence interval. What I can say then is, well, okay, if I, don't have any information, or I'm just going to assume that it's a symmetrical reward distribution, I'm just going to assume then that without any more information, I'll do the most sensible thing, which is probably going to be to take the median. Okay, well, the mean. Okay, well, if that's the case then that's probably a safe thing to do. However, perhaps it's the case that actually I get a higher reward if I underestimate rather than overestimate. Well, then instead of choosing an action that would correspond to that mean, instead what I'll do is I'll kind of pitch a little bit lower. Conversely, if I have a reward distribution that is skewed in the other direction, I'm going to pitch it a little bit higher because, okay, if I'm completely right in my choice, then it's going to be, I'll get, in this case here, I'll be fine. But actually, there is a little chance that it could be higher. So in that case here, I'll just pitch a little bit higher, and then, mathematically, I know that if I convolve these two distributions, that's going to be my maximum. Okay. So, I've talked about sparse data. I've talked about how sparse data can be efficiently used by probabilistic models. And I've talked about how probabilistic models themselves are fantastic because they quantify uncertainty, and uncertainty itself allows us to choose decisions where we know the reward distribution, or even if we don't know the reward distribution, because we can look at the entire space. Okay, that's all very well in theory. What does it look like in practice? So I'm going to talk now about a case study, which is some work that we did within supply chain management. Disclaimer, a year ago I had no idea about supply chain management, and if you yourself have no experience of supply chain management, you can really think of it as logistics. How do things move around in the world? This is a multi-billion industry. It is responsible for making sure that everything that you are wearing, that you are sitting on, that is around us, got to this room from raw goods, right? So it's very complex, very convoluted. If you are interested in the details, I'll be sharing a link at the very end about the white paper that we have about the supply chain, and you can read through, but this is just to really give you an overview, and I guess kind of to lift the lid on how we approach this problem. So first of all, what was the problem? So the problem was pallets. The experience that I had with pallets until this point was as hipster furniture in cafes. That was about it. I never considered an ecosystem that happens behind the scenes, but now that I know about it, I can't stop seeing pallets everywhere I go. So I'm going to explain it to you in one slide. So the kind of the ecosystem of pallets is that there's a warehouse somewhere where all the pallets are made, created, stored. They then get shipped out to manufacturers. So these are your Coca-Cola, your Unilevers, your really, really big people big companies that make things and then want to send them out to supermarkets or whatever retailers that are out there. So the pallets end up at the manufacturers. The manufacturers make their goods, load them on the pallets. Those pallets then get moved out to retailers. And the retailers will unload the goods off the pallets, put those goods in their store, and then throw the pallets out their back, either in their yard or sometimes outside the yard too. So the client or the customer that we worked with here were the people that made the pallets, right? So what was interesting was that they made the pallets. They were responsible for getting them from the plant, the pallet plant, out into the manufacturers, and that was the end of where they saw them until they wanted to pick up the pallets at the retailers and then bring them back to the plant for either repair or just to be reused again. What's interesting about this problem is that they had no visibility what was happening in this middle cloud section, which is exactly why we've represented it as a cloud. They wanted to know where the pallets were. They weren't sure where they weren't always sure where they were though. So there were kind of three main challenges that we had. And I should say the aim of what they wanted to be able to do was to reduce the number of failed collections from retailers. So because there was no information about what was happening here at each of these retailers, they were calling their transport companies to go and make a collection at retailer A. The transporter would turn up there, and sometimes there would be pallets. More often there would be pallets, but sometimes there would be nothing. And then the haulier would go back home and they would be grumpy because they weren't getting paid for it, but ultimately, the customer that we were working with did have to pay for it. It was actually really, really expensive to have a failed collection, and they were finding that for some retailers there were a large number of failed collections, which is a bit crazy. So there were three main challenges that we had. The first was that there were no stock counts at these retailers. So if there were stock counts, each of the retailers could track each day. Yeah, today I have 50 pallets. Today I now have 150 pallets. This would be a really easy problem. The retailers had no motivation to do this. They just wanted to get on with selling their goods, right? The second problem was that you could say, sensors are really, really cheap now, and we'll just stick a sensor on each of the pallets. We didn't have that either, and we kind of raised whether this was a possibility, and they said no, it doesn't make sense. Pallets cost somewhere between $15 and $20 to produce each pallet. Think about that next time you're in your hipster cafe. But an RFID sensor is about $5. It doesn't make sense to kind of, from our perspective, to go through and stick that on. And also then you need all the infrastructure around in order to track pallets too. So in reality, they had no idea where the pallets were. The second challenge that we had was the data that was available to us. The first, so I'm just going to put up that kind of snapshot there. So the first sort of data that was made available to us was this movement from manufacturer to retailer. So that was the delivery data. So the customer that we were working with wasn't responsible for that, but they had some access to some sort of data that was passed on to them. However, because it was passed on to them, it wasn't there from their origin. First of all, it wasn't always correct. And secondly, it could be up to a year out of date. If you're asking me to make a prediction about what's going to be happening, early next week based on data from a year ago, you need a very, very good model. And I don't think there's any model in the world that can, look at what was happening a year ago in order to, without any sort of information in that intervening period. The other type of data that we did have was collection data. So this was when trucks turned up, or lorries, I should say, turned up to the retailers. They would say, yeah, it's good, or yeah, it's not good, and we had a failed collection. That was good, but again, it didn't tell us how much stock there was at each of those retailers. The third problem that we had was that there was a lot of different sorts of retailers. Hello. So there's different retailer sizes, so from your super Tesco's to your corner stores on the side. But there's also different sorts of retailer behaviors too. So even with the large retailers, they can behave very differently from each other. So we needed to have a model that could adapt to both the size and also the behaviors of the different sorts of retailers. So our approach was to take the collection data, because that was the best data that we had available. We didn't know at first, how that was going to work, and it was interesting to predict something that was different to the type of data that you had. We combined that with probabilistic model, of course, and from that we had a prediction. So the prediction was, what stock level do I think I will have during the coming week, and with what certainty? And from that prediction, we made a decision, when should I attempt a collection, and how certain do I need to be in order to schedule a collection? So this is what the data looked like. So what we have here is across different weeks, we have a number of, the green bars represent the number of pallets that were successfully collected, the red, those that were a failed collection. And the way that our model worked is to go through and say, well, okay, there was some dynamics to capture how pallets arrived and how pallets were taken away, and also some internal dynamics too, as well as a noise term. And it was basically trying to fit through. And you can see already it was, there's a little bit of uncertainty in periods where there's not that much data, but it, covered quite nicely. And this was actually quite a dense example in comparison to some of the retailers we had. We only had, over a 4-week period, we may have only had 4 observations. So once the model fit, we said, okay, well, what's going to happen over the next week or so? And we get some sort of, so these are the raw traces, right? So in reality, we tended to look more, okay, well, what was the mean, and actually what was the 90th percentile? So this is the sort of way that we kind of said, okay, this is how the stock is going to accumulate if we weren't to do anything. But we do want to do something, and the thing that we want to do is organize a collection. And one of the things that you might notice is that it's kind of quite quantal here. There's each of these bars that corresponds to 1 truck's worth. That difference there corresponds to another truck's worth. From a hauliers point of view, they want to have only full truckloads when they go back. So these are the kind of the choices that we had. Where do we think what makes the most sense to schedule if we're going to schedule a collection for tomorrow? Well, I guess anywhere from here to here would have made sense. Because we know that there was so much cost associated with a failed collection, we always said, okay, well, we'll take the median, but perhaps we'll be, we certainly won't go above the median, we'll go, on the lower side of the median. So if we choose this then as our collection schedule, or proposed collection for tomorrow, we can then go through and rerun the model again and kind of progressively keep on doing this and build up a collection schedule over the week. Okay, so that's really quite, that's not rocket science at that point. That just becomes, but there's a lot of nuance in there too, and especially at this point it was interesting because it stopped being a Gaussian process. It started to have other properties in there too. So, as I mentioned, there's this kind of question about, what's the most robust decision you could make? Well, okay, if you're really keen on avoiding failed collections, you're going to go for, if this is your median, if you want to avoid failed collections, you're going to undershoot. If you want, however, to recover stock, if you want to make sure that there's not stocks that's sitting there at the retailer, you're going to, I guess, overestimate, right? You're going to say, okay, well, I'll go for 3, maybe 2 or 3 collections for the next day, because I want to try and get that stock that's sitting there idle back in. So what was the impact that we saw? Well, first of all, I guess what was interesting, certainly for us and certainly for the people that we were working with, was, or the company that we were working with, is that for the same sort of Gaussian model, the same basic function, we were able to represent different sorts of retailers. We were able to account for model size, different behaviors, and that actually these were directly reflected in the parameters that the model fit to. And this was really useful for us, ended up actually also being really useful for them too. The second thing that was interesting was, or impactful, I guess you should say, is that we actually showed that we could improve collections. So our proposed collection schedule would have reduced failed collections by 33%. There were still times that we overshot just a little bit. But as certainly as we went on, that kind of weekly proportion of failed collections certainly went down. We only were evaluating for 5 weeks. So And the last thing that I think was the most, as a surprise to me was, okay, that actually one of the biggest inputs, change or impacts for the customer was that actually, until this point, they had no idea what their stock count was at each of these retailers. If you remember, there was no stock audit, so they had no idea. By going through and fitting this model, what we were able to give them is some sort of idea about what their stock could have been, what range it was in, and that also allowed them then to say, well, okay, this is how much stock is then sitting there idle, unused. Oh, actually, maybe we should go out and be a little bit more proactive in kind of getting that back in again. Okay. And I think that last point too was quite interesting. So in terms of decision making, we think of decision making about I'm making one decision. But I think one of the valuable things about probabilistic models is that they actually allow us to compare prospective decisions over a parameter space. So if this is, we're looking at, collection failure rate versus the amount of stock level. And for both of those, if we go too far this way, we're going to have more failure costs due to failed collections. If we go this way, we're going to have stock that's sitting there at the retailer, so we're going to be increasing our CapEx costs, basically. We can go through and say, okay, well, actually, what does our probabilistic model tell us about how do these two things look in comparison to each other? So this is just a kind of illustrative example, but certainly we saw this sort of shape for the retailers that we were looking at. If we then kind of go through and say, well, okay, a robust decision, the default robust decision would be, okay, well, I want to try and have no failed collections and minimize my stock as much as possible. Fine, great. However, if you're the decision maker that's sitting there in within strategy, you might say, well, actually, maybe it's okay to, leave stock sitting there a little bit longer. I really want to be quite conservative in my approach. Or maybe you say, well, actually, I've got so much stock that's tied up, I actually want to be really aggressive in my collection strategy. I want to go out, I don't care about the cost of failed collections, I want to go and get that stock back. So, using this sort of principled decision-making allows us to go through and investigate the different implications of these strategies a priori, which, from the point of view of the decision-maker was really attractive and something that they hadn't, conceptually been able to see these two things linking together before. So, in summary, what have I talked about? So I've talked about a lot of things. So I've talked about the problems of big data and that not being able to solve all big problems. I've talked about how if we're going to go through and get around this problem as an industry, we need to be looking at more efficient models that will allow us to go through and work with sparse data. I've talked about how probabilistic models can do this, and furthermore that they can also go through and show us the uncertainty, and that uncertainty is really important when it comes to making a robust decision. I also went through and showed how this actually works in real life, so that probabilistic models can handle many of these ambiguities in real-world challenges, including those of supply chain management, where we use GPs or Gaussian processes to model and decide when to schedule. And by doing so, our proposed schedules would have reduced failed collections by 33%. By showing the potential schedules also allowed decision makers within strategy to work out what kind of trade-off they were willing to take between failed collections and stock sitting there. And lastly, there's an applicability to having Gaussian processes that allow us to infer variables and parameters that aren't easily estimated in the real world too, because they automatically come out of the models. So I'm going to leave it there. I'm going to thank you very much for your attention. I think we have a little bit of time for questions. The case study is available on our blog. As I mentioned, we are recruiting for enthusiastic, talented data scientists. We're here tomorrow at the recruitment fair. Please come and find me afterwards for a chat though too. And I'll be happy to answer any questions.